Hello, I'm the Reverend Robert Thomas Malthus. I was born on the 13th of February, 1766 in Dorking, Surrey. My best known work was the pamphlet essay on population, which I published in 1798. In it, I argue that unchecked population growth would outstrip the food supply available.
Hello, this is Mr. Ferris. I know you were expecting me at the beginning, but what you heard was from Thomas Malthus, who was an economist who made a fairly interesting prediction about the future back a while ago. And one of the things that is relevant to what we're studying is that he talked about the power of population. He was really talking about population growth. The power of population growth is superior to the power to produce substance. And you might imagine that since it's about population growth, he was referring to exponential growth. And exponential growth, of course, is what we are studying in this chapter. So he had some thoughts about exponential growth compared to other types of growth, which generally we might consider to be linear, and the ramifications. And you can probably figure out what the ramifications are when population grows exponentially, but food sources perhaps are only growing linearly. We'll come back to that a little later. As we've seen in class, there are a lot of instances in life where data would produce growth that perhaps is exponential. For instance, it's not a big surprise to think that cell phone growth perhaps has been exponential in different parts of the world. This happens to be the Arab world data, and the subscriptions per 100 people appears to have been growing exponentially from about 1995 to 2010. Whereas in Korea, for instance, the growth has been a little more linear. And so this is just an example that there are instances where we have data, and some data maybe would suggest exponential growth, other data may suggest linear growth. And one of the roles of mathematics, of course, is to model that growth pattern the most accurate way possible so that people can make predictions and make calculations. But of course, not all data is that simple. Here we have the country of Turkey, the cell phone subscription rates again, and it does some goofy things. It kind of speeds up, and then it slows down, and then it speeds up again. And then there's been a downturn, and now a little uptick, and who knows what kind of model that would be. That would be a little more difficult to work with. Fortunately, we're going to stick to some real simple and foundational modeling issues. So for instance, what we might be asking you to do is to take a table of data and answer two different questions. First of all, which of these two functions is linear, f or g, and then which of them are exponential. And so I hope that it would be pretty quick to figure out the linear one. As we can see, our inputs, thankfully, are going up by 5 every time, so that's going to make it easy to analyze. Since our delta x for everything, basically, our delta x is always 5, then it's going to make it real easy to determine, even just by looking, perhaps, which is linear and which is exponential. So for linear, just a reminder, we're looking for a constant rate of change, and it's going to take us probably less time to figure it out than it is for me to write it. If you look at the outputs on function f, you'll notice the outputs are increasing by 15 every time x increases by 5. F goes up by 15, x by 5, 15 and 5, 15 and 5, 15 and 5. So clearly the rate of change for function x, or function f of x, just by doing a quick calculation, everywhere we checked it, it was the difference in function values of 15 and difference of x values of 5. Everywhere we checked it. And so since the constant rate of change is 3, we know for certain that f of x is linear. That's a pretty quick check. And of course, it was made easy because x increased by 5. Now, a word of warning, that may not always be the case. So you do have to pay attention to this. You cannot just look at f of x to determine what kind of function it is. You also must check the difference in the x's. And if in the future, I can pretty much guarantee that you'll see this, if in the future x does not go up by 5 every time, but maybe goes up by 5 and then 3 and then 6 and then 1, well, then you'll have to do a little more careful calculations. It will not be just as easy to look at at the outputs. So now if we turn our attention to G, we're of course expecting G to be exponential. And if that's true, then using our definition, it's no longer about rate of change, but rather the percent change, or may we say the ratio of change. Now again, it's been made easier because the differences in the x's are constant. So x is increasing by 5 every time. That's going to make it quite easy to see if we have some sort of common growth factor. Now the easiest way to figure the growth factor, especially since this is these numbers are listed here kind of in an ordered pattern as x increases by 5, is to divide in this direction. So if there is a growth factor that's the same all the way through, then what's going to be true is that when we divide 1200 by 1000, we're going to get 1.2. That's the growth factor, at least between when x is 20 and x is 25. And if this growth factor is constant all the way through here, why then we know that this is an exponential function. So now if we divide 1440 by 1200, do that on our calculator, we'll notice that's also 1.2. So now we're getting suspicious that it's always going to be 1.2. And so it turns out that the ratio, or the growth factor, between successive outputs is always 1.2. Now, I use the term growth factor kind of loosely because if we were writing an equation for g of x, 1.2 would not be the growth factor because that's only the growth factor for every 5 x's. For every increase in 5 in the x, the factor is 1.2. Now, if we were going to write an exponential equation for this, then our growth factor, which would go in this position right here, our growth factor would not be 1.2. We would have to find out what the growth factor is for every increase of 1, and that's a little more difficult question. And it's not going to be 1.2. It'll be something a little less than 1.2. So just a word of warning, the growth factor I'm talking about is just a kind of a general growth factor that I'm using to assess whether or not g of x is in fact an exponential function. So for every delta x equals 5, my growth factor is 1.2. But that would not be the growth factor if I were writing an equation, so just keep that in mind. Now, having done one example, hopefully that would give you enough reminders to do 4 more examples. So what I'm going to ask you to do is to complete 4 problems on page 116. And in lieu of a little quiz that we normally have, what I'm going to have you do is do those 4 problems and hand those in when you come back to class. Those are all tables, and those are all writing equations from data in tables. And of course identifying which type of function it is first. All right, now let's do an application problem talking about some turtles. It said at some time in the past, at time 0, some turtles were released. Now we do not know how many, and that's we're going to come back to that in a little bit. We don't know how many, but we know some turtles were released into a population or a forest or something, or a pond. And 4 years later, however, they come back and they estimate that there were 300 turtles. And then 3 years later, 3 years after the 4 years, they estimated the population has grown to 450. So it's clear that the population has grown from 300 to 450, and we're going to let P be the population, and the year is going to be T. And we would like to try to figure out what kind of growth is going on. Well, if you would graph it, you would find this. Not much information. We just get 2 points. There's a point at essentially 4, 300. That's where that point is. And then 3 years later, which would be at year 7, this point is at 450. So we don't have a whole lot to go on. If you only have 2 points, that's not really a lot of data, and that's not much to go on. So the question that we might ask is, well, what kind of growth is this? Now, I suppose your eyes would suggest that it's linear growth because between any 2 points, of course, there would be a line. So yes, that's possible. It could be that was linear growth, a certain number of turtles per year. But that's not the only model that would work. It is possible, actually, to fit a exponential model through those dots. So there's actually a possibility that there's a curvature here. And so maybe the initial amount was actually up here. With the linear model, you get an estimate of the initial amount somewhere down here. But if, in fact, an exponential model is correct, well, then the number that we started with was probably a little higher than if we assume linear growth. And so notice both are legitimate models when you don't have any other information other than it's turtles. Maybe turtles do grow linearly. We don't really know for sure. So the bottom line is you can actually do either model, and you will be asked to do either model. And so that's the next question. Now, for a linear model, I'm pretty sure that you should be able to do that. You have the skill set now, and we've practiced this in other examples, to take two ordered pairs like 4, 300 and 7, 450, and you can write a linear equation. Remember, P is population, and T is time, the year, time. And so your job right now, and I'm assuming you'll have the discipline to do this, is to pause the video and take a piece of paper and do the necessary mathematics, algebra, and figure out the slope and y-intercept and get the linear equation. I'm assuming you can do that, and I would like you to do that right now. Assuming you were able to complete a little Algebra 1 problem, I will now walk you through how you find an exponential function. If this is in fact exponential, why then it's going to have the format for an exponential function, which would be t equals some initial population times some growth factor to the t. Now I meant to put a p there because p is population and little t is time. This is the template that the exponential function will have. So instead of finding the slope and the y-intercept like we would do with linear equations, instead we want to find the initial amount and we want to find the growth factor. Now the initial amount, remember, we don't know. It just says some turtles. We don't know what that was. So we can't go by that, but remember we do still have two ordered pairs. We know that at 4 years there were 300 turtles, and we know at 7 years there were 450 turtles. And so what we can do, since we have two ordered pairs, we can write two exponential equations. And so my advice is always to write the one first that would have the larger x, and you'll see why later, the larger input. So my suggestion then is to plug in 450 for population first. The population equals a times b to the t. Our first t is 7, and I always think it's better if you write the first equation as the one that has the larger exponent. And then if we substitute 4, 300 into the same formula, 300 would be our population, and that would be, again, a times b to the 4th power. And the reason that we write, at least I think it's easier to write equations so that the larger exponent is on top, is because of what we're going to do next. These are two equations. We have two variables. And back in algebra, when you used to solve two equations and two variables, usually you would have a sum or a difference. Instead of a times b, it might be a plus b. And we didn't have exponents either. So this is not exactly the same as you did in algebra. With algebra, you would do this with linear equations. And now we're asked to do this with exponential equations. But our goal is still the same. Our goal is to eliminate one of these variables so that we can solve for the other one. And in algebra, you used to eliminate variables by adding or subtracting. But since this is a multiplication equation, has some multiplication in it, the hopefully reasonable and logical thing to do is not to subtract or to add, but rather to divide these two equations into each other. And when you do that, you will be able to eliminate a, because a now is a common factor. And if it's a common factor, then it will cancel. And now we have to remember our algebra skills. So first of all, 450 divided by 300 will be 1.5. And now we got to remember that when you divide b to the 7th by b to the 4th, the rule is you subtract exponents. I hope that's what you were thinking. So we will get b cubed equals 1.5. And when you solve for b, take the cube root. Turns out that b is approximately 1.145. So that process of plugging in both ordered pairs and then dividing the equations will allow us to find the value of b. That's our growth factor. And now what we want to do is take this b number and plug it in up here. Actually, we want to plug it in, take your pick. Plug it into one of these two equations. It doesn't really matter. If we plugged it into the second equation, we would get 300 equals a times 1.145 to the fourth power. We're plugging it into this second equation. And if you trust me here, if you solve for a is going to turn out to be 175. And to solve this, all I did was take the fourth power of 1.145 and I divided it into 300, and it turns out it's 175. So our final answer for this one is going to be P equals, population equals 175 times 1.145 to the T power. That's the equation that would model this behavior if the population growth is in fact exponential. And with that, of course, then, that would mean that we would assume, oh, they must have released 175 turtles back at time 0, and then the growth factor is 1.145, which indicates about a 14.5% growth rate per year. So if in fact turtles are growing that way, this would be our description of the growth. All right, so here's a follow-up question. You did the linear equation for those 2 points, and I did the exponential equation. So the question I have for you then is, all right, when time gets out to 12 years, they counted 900 turtles. Now we've got 3 points. Remember we started with 4,300, and then we got 7,450. Well, now there's a third point, and this third point is now going to probably verify one of those two functions. If it's in line with these other two, well, then linear model is probably appropriate. But if that point is maybe a little higher and indicating that, oh, maybe this is curved, well, then 12,900 might seem to fit the exponential model. So your job then is to figure out which model seems to fit better. And I'll let you do that, and that will be one of the questions that you should answer for this video. And now we're going to do another example where we want to take a couple tables, decide what type of function it is, and create the formula for each. So this is the kind of thing that you'll be asked to do frequently. And so the first one is not really too hard because I think you can tell. Because x is increasing by 1, by 1, by 1, by 1, and because the outputs are increasing by 10, by 10, by 10, by 10, this has a constant rate of change. Therefore, it's linear. And the rate of change is 10 over 1. Because the outputs are increasing by 10 every time x increases by 1. So if we were going to write a formula for that, I think we could probably do that right now because the initial value is sitting right here. The initial value when x is 0 is 65. That would be like our y-intercept if we were thinking of the graph. And then since our slope is 10, this would be the equation. So the linear equation is really not too hard to figure out. We've done this for many years now. So the function x was linear, and that was the formula for it. Now let's turn our attention to the exponential function. Exponential functions, remember, have a particular format. They are going to look like this. It'll look something like g of x equals a times b to the x, and our job is to find a and find b. Well, this one's a little bit easier because a is sitting right here. The initial amount is sitting right there. When x is 0, g is going to be 400. So this one turns out to have a little less work involved since the initial amount was given to us right in the table. So now all we really have to do is just take another ordered pair, one of these ordered pairs, and plug it in. And I would certainly recommend this one right here because of the numbers involved. So if we put 600 in for g of x temporarily, and we plug in 1 for x, then it's going to be pretty easy to figure out b, I believe. So when you divide both sides by 400, you'll find that b is equal to 1.5. 600 divided by 400 is 1.5. So the formula is going to be that g of x equals 400 times 1.5 to the b power, or to the x power. There's the formula for the exponential function. This one was made quite easier because the initial amount was sitting right here. If that was not the case, we would have had to written two equations with two variables. So if you want some extra practice, you could take, let's say, these two ordered pairs, and you could do that same technique I just did, where you write two equations and you divide them into each other and do it that way. So just be on the lookout for problems that are easier. There's no sense in doing the hard stuff if you can see the initial amount is 400, and then you can plug in an easy point right there. So there are some ways to do problems easier if you're able to look at them and not just be stuck in some mode where you think you have to find all the steps. Now, back to the man that opened us up. Thomas Malthus said that he believed population growth increased faster than the food growth. And so what if we thought about this? Let's just make a for instance. What if we had a 2 million population, so the initial amount is 2 million people, and we're growing at 4% per year. And then what if we assumed, or somehow we're able to figure out, that food supply started out at 4 million. We had enough food for 4 million people, but it increases linearly at 500,000 per year. Well, the population formula is pretty easy to write. The population formula would be P equals 2 million people times, if it's a growth rate of 4%, then our growth factor would be 1.04 to the t power. And then the food formula, we've got enough food to feed a population that starts at a brief power failure. So now we're back. So it starts at, you have enough food for 500,000 people, and it grows linearly. Actually, okay, I messed that up. It starts at 4 million people and grows at 500,000 per year. So here we have two equations. One of them is exponential, one of them is linear. And so maybe you can imagine this. You've got one equation that starts at 2 million but grows exponentially. And you've got another equation that starts at 4 million but grows linearly. And I think you can kind of tell what's going to happen eventually. Maybe you can presume or maybe see that eventually the exponential graph is going to overtake the linear graph. And I've actually done the graph on this, and you can too. And I would suggest that it would be a good chance to use your technology and see if you can reproduce this on your technology, either your Texas Instruments or Casio or whatever instrument you have. So graph these two functions. There's the exponential and there's the linear, and see if you can get a window that would produce this intersection, showing that in fact the exponential equation will eventually, it may take a while, but eventually it will overtake a linear. So if Thomas Malthus is correct, then eventually we may have a problem. We may have population of the world that grows faster and overpasses our ability to keep up. Now, he said some other things about natural deaths and other events that would perhaps stem this tide, but you can always Google him if you want to find out more details about that. But mathematically, that is a fact, that exponential functions will overtake linear functions eventually. So your final assignment would be to finish all the work that was asked for in the video, and then as always, you should see Canvas for any additional information. I'll see you in class.